Okay, so section 1.2 is all about functions and graphs. So we're going to look at the difference between a relation and a function, and then we're going to look at finding domain and range of functions and relations, and then we're going to look a little bit at evaluating functions, okay? So when we talk about a function is different than a relation because it has an added stipulation, okay? A relation has no stipulation. It's just any correspondence between a first set of items and an output set of items. So an input and an output, or X's and Y's, or any type of correspondence or relationship between two things could be called a relation, right? And the set of inputs is what we call our domain, and the set of outputs is what we call our range. Okay, so here's examples of two relations, and we want to go ahead and find the domain and range of each. So remember, the domain is our set of inputs, or our first set, right? And the range is our outputs. So on this one, if I wanted to list my domain values, it would just be 2 and 9. And we do it with set notation, because we're not saying it could be 2 to 9 and everything in between. We're saying it's just 2 or just 9, right? So that's why we use the little squiggly brackets, okay? Same thing with the range. If we want to list the range here, the range can only be -5, 5, or 4. And we always write them in order from smallest to largest. So -5, 4, or +5, okay? And the same thing is true if they are giving us our relation as a set of ordered pairs, right? This would be my input, or my X, and my output, Y. And our domain is our set of all first coordinates, or the first set of values, or our input. So here our domain values would be all of our X values, right? So 1, 3, 1, and 2. So 1, 3, 1, and 2 means we have two ordered pairs that have a 1. We don't have to list it twice, okay? So 1, 3, 1, and 2 really just means we have 1, 2, and 3 as our potential X values, our potential input values, right? And then for our range, we do our output values, which is our second coordinate. So here we have 3, 1, 2, and 2. So we don't have to list the 2 twice. So 3, 1, and 2, and then we write them from smallest to largest. So 1, 2, and 3. Okay, not too bad. All right, so now let's talk about a function. A function is a relation, right? It's a relationship between inputs and outputs, or X's and Y's, but it's specific, and that when we talk about our function, every element of our domain, or our input set, gets tied to exactly one member of the output set, okay? Or in other words, every domain value has exactly one range value, or every X goes to specifically one Y, okay? And the way that we can test for this is we can use the vertical line test. The vertical line test is also referred to as the pencil test, which means if you put your pencil down on the graph, wherever the graph is, it should only hit the vertical line or the pencil one time. If it hits more than one time, then it's not a function, okay? So we'll look at that when we look at the actual graphical representation of functions. So for now, here's some examples, and I'm going to just compare this one with the relation we did up here. Notice every single domain value only goes one place. You can think of it like an airplane. If these are people and they go to the airport, they can only get on one airplane and go to one destination, right? So here, person 9 is going to 5, which is maybe Hawaii, right? Person 2 is going to Hawaii. Person 3 is going to Nepal, right? Or wherever, because each person can only get on one plane and go one place. But if you look at the relation up here, notice it shows that 9 is going to this destination and this destination. It's not possible for one person to fly 2 places at the same time. So that's what makes this a relation and this one specifically a function, because every domain value goes to specifically one range value. Okay, so again, we just want to go ahead and highlight the domain and range here. So our domain values are all our input values, and we write them from smallest to largest. So this would just be 1, 2, and 9. And our range values are our output values, again, from smallest to largest, so 4 and 5. And we're using our little squiggly braces because we're not saying it goes from 4 to 5 and everything in between. We're saying it's just 4 or just 5, right? Okay, so let's look at it when it's given to us as an ordered pair, a set of ordered pairs. Our domain is still all our first coordinates. So here our first coordinates are 1, 3, 4, and 2. If I list those in order, it would be 1, 2, 3, 4. And when I look at my range values, that's the set of all second coordinates, which here would be 3, 1, 2, and 2. Again, I have double 2s. I don't have to list them twice, so just 3, 1, and 2, or in the correct order, 1, 2, 3. Okay? So same as above. Now, when we look at pictures like this, we're going to assume that if the graph doesn't stop with a closed dot or an open dot at the ends, then we're going to assume it keeps going, okay? So we're going to go ahead and write in those arrows just to make sure we know that it keeps going. So when we look at our domain, that's the set of all input, right? And input, when we look at a graph, is our x's, right? So this is our negative x direction, this is our positive x direction. So when we look for a domain, we're really asking over what x values does our function cover this graph, right? So notice if I start like somewhere in here, I can see any of these x values, I can map them up and find a point on this graph, right? Even as I go out in the negative direction, I can still map this down and find points that are going to fall on this line, right? And because there's an arrow, I know this is going to keep expanding out and out and out and out and out and out. So no matter how far I go to the left, I should always be able to map down my x value and find a point that hits this graph, right? So that means my domain goes all the way out to negative infinity. And from negative infinity, as I travel this direction, notice all of these x values are defined, right? This x value has a defined point, this x value has a defined point, this x value has a defined point, right? No matter how far I keep walking, I can still find x values, right, that have defined points on this line. So, and that's going to continue on because this line is going to keep going and going and going. So no matter how far out on the x-axis I go, I should be able to map it up and hit a point on this graph. So I'm going to use interval notation to represent this domain because all of my x's are included. It's not just this x or this x or this x, right? It's all x's. All x's from negative infinity to positive infinity have a representation on this picture. Okay, and then we want to look at our range. Our range is our output, right? And output, when we have it graphed on an xy coordinate, is our y values. Okay, so if I look at my y's, this is my negative y direction. This is my positive y direction. So I'm looking at how low does this picture go. And you might say that it ends at this point, right? Because that's the lowest point on the curve. But even though this curve only goes here, notice this whole piece is still part of the picture and it's actually going to keep going down. So no matter how far down on my y-axis I go, I should always be able to map it over and find a point, right? No matter how far down I go, because this is going to keep going and going and going. So that means our range can go all the way down to negative infinity. And then how far up it can go is the highest y value that it's defined for, right? Because this piece is going to cover all y values from negative infinity up to this point, right? That's the highest point on this little part of it. But then notice where this one ends, this piece is still defined for that y value and all y values that are above it. So this is actually going to go from negative infinity to infinity because I'm covering, my picture here is going to span across all negative y's and all positive y's. And there's no gaps of coverage in between, which means every y from negative infinity to infinity is going to be covered by this picture. Okay. All right. So let's look at this one. This one's a little bit different. So again, our domain is our x's. We're looking from the negative x over to the positive x to see how far is this picture going to cover that way, how far is it going to cover that way. So again, for my math lab and the purposes of this class, unless you see a dot, see how this one has open dots? I don't know how good you can see it, so I'm going to write them bigger. Here's a big O open dot. Here's a closed dot. Here's a closed dot, right? But notice there's no dots over here. So we're assuming that this end is going to keep going and this end is going to keep going. So the first thing we need to know is how far in the left and right directions are my X's going to be defined for this picture. Well, this piece right here alone is going to tell me that I should be covered all the way out to negative infinity, because this one's going to keep going and going and going, right? So from negative infinity up to what? I need to see if I have a break in coverage. So from negative infinity up to what? This looks like about -2 maybe. That's where this piece ends, but notice it has a closed dot. So it actually is defined at -2. And then things beyond -2 are actually defined on this next piece, right? So notice I don't have a gap in coverage here. Even though it jumps up from this line to this line, we're talking about X values. So you can think about this as like a little guy walking, and I'm trying to figure out where can he walk and still have clouds above his head. So if he's walking from negative infinity this direction, right, he has this cloud covering his head up to this point. And then after this point, this cloud picks up and covers his head, right? And notice there's no gap, because even though this one doesn't include -2, this point does include -2. So the sun can never get to him, right? He's covered by cloud coverage. Same thing when this cloud ends, if he's still walking under here, right? When this cloud ends right here, this one picks up. So again, the sun can't get through to him because he's covered under the top cloud, right? So as he goes on, this is going to go on out to positive infinity. So even though there's 3 pieces or 3 parts to this graph, when we look at it as a combined picture, the X's are covered from negative infinity to positive infinity. Let's look at the Y's for our range. If we look at our lowest Y value, it's not going to be like this other picture because I don't have an arrow going down, right? This arrow goes out to the side. So this line itself is my lowest Y value, right? And my lowest Y value is down here at -2. And notice it's not like from -2 to up to some other Y value, or from -2 down to some lower Y value. It is a straight horizontal line, meaning it is just -2. So if it's just a number, not a span of numbers, then we're going to use our set notation with our squiggly brackets. So it can be just -2, or if I look at my next horizontal line, this is just +2, right? So any Y value that lands here is just taking on the Y value of 2. So I can include it in my set notation. Or my third piece up here is at, I don't have to drop my lines in, 1, 2, 3, 4, 5, right? So this line is Y equals 5. So when we use set notation with the squiggly brackets, this is saying the possible outputs or the possible range values. If we pick any X from negative infinity to infinity, our possible Y outcomes are either going to be -2 or 5. There's no other possibilities for Y values on this graph. Does that make sense? All right, so on the next page, there are 6 for y'all to try. So the first thing is we want you to determine if it's a function. So you can either write function or not a function. You can write yes or no, but I want you to determine if it's a function. We can use the vertical line test. Remember, if we draw a vertical line anywhere on it, if it only hits once, then it's a function. If it hits more than once, then it's not a function, right? So regardless if it's a function or if it's not a function, we want to find the domain and range of each of these 6, okay? So go ahead and do that. I'll give you just a minute and then we'll go over them, okay? All right, so let's go ahead and look and see how you did. So on the first one, is this a function? Your answer should be yes, right? Because if I lay a pencil anywhere down on here, it's only going to hit at one point. Or if I draw a vertical line anywhere through this graph, it's only going to hit at one point, right? No matter where I draw a vertical line, it should only hit at one point. So that means that yes, it is a function. And then we want to go ahead and identify the domain and range. So again, you can think of your little guy walking along under here. Where is he going to have cloud coverage? Notice these don't have arrows on them. So it is only from this defined X value over to this defined X value. Or in other words, if he's walking along here, he only has cloud coverage from -4 until he walks over here to +4, right? And since we have closed dots, that means that we're going to include our endpoints. So we're going to use interval notation to say it goes from -4 to 4 and everything in between. Okay, don't use the squiggly ones. Use the brackets to show that this is interval notation, meaning it includes everything in between. Okay, same thing with our range. Our range is our lowest Y value all the way up to our highest Y value. So our lowest Y value is this point right here, which is down here at -4. And notice it's not just that point and just this point and just, right? Every Y value from -4 all the way up to +4 is included on this curve. So again, our range is going to be from -4 to 4 using interval notation to show everything's included, and we're using brackets to show that the endpoints are included. Okay, let's look at our second one. If I draw a vertical line through this S curve, right, notice it's going to hit 1, 2, 3 times, or 2 times in some places, right? So it's not a function. Not a function if it hits a vertical line more than once. Okay, so not a function, but we can still find the domain and range. Again, if I think of my cloud coverage when I have a little guy walking along here, notice this S is only going to cover him starting at X equals -2, right? This is the first place we see a cloud above his head, and then he'll be covered all the way until our S ends, which is over here at +2. So our domain should go from -2 to +2, and because they're solid dots at these points, right, that means that those values are included, or they are defined for this function, or it's not a function, sorry, for this relation. So we're going to use brackets to show it goes from -2 to 2, and the range, same thing. Our lowest Y value is -4, goes all the way up to +4, and every Y value in between, I could potentially map it over, right, to a place on this relation. So -4 to 4 with brackets is going to be my range for that one. And then I look at my second one, my third graph here. If I do the vertical line test, it's not going to pass, right, because it hits twice. So this is not a function. When I look at my domain, I'm looking what's the furthest to the left I can go and have cloud coverage. Think of your little guy walking down here, right? So this cloud starts right here at X equals -2. And then as he continues walking, right, these clouds keep going and going and going. So it should be from -2 to infinity. And because there's not an open dot right here at the top of this sideways parabola, then we know that that point is included. Okay, so we're going to use a bracket on the -2. Range is going to be all real numbers, because this side is going to keep going down and down and down and down and down to span across all negative Y values, right? This side is going to keep going up and up and up and up and up, which will eventually span across all positive Y values. So our range has no restrictions from -infinity to infinity. Okay. Our circle, when we draw our our vertical line test here, it's going to hit twice. So no, it's not a function, but we can still find our domain and range. Our domain, this oval, is going to go from X equals -4 over to +4. And notice every X value is going to have a representation on the curve. So we're going to use interval notation and brackets because our endpoints are included. Same thing with our range. It goes from -3 up to +3, and every Y value is included here because of the curve, right? So we're going to use brackets because every point is included. All right, everybody okay so far? All right, then the last one is kind of like the first ones I did, where they just show it as a plot or as a chart, right? And this one is going to be a function because you can see 14, 3, and 1 are all going to exactly one place. Now, it doesn't matter that 14 and 1 went to the same place. We don't care. All we care about is that 14 is only going one place, 3 is only going one place, and 1 is only going one place. So yes, this is a function. My domain is all my input values, 1, 3, and 14. My range is my output values, which are 6 and 7. Okay. Same thing on this one. This one's not a function, however, because z is getting sent to u and also to y. Now, I didn't mention this earlier, but you will see some like this in your homework that don't have numbers. They just have letters. So if you're given numbers, we want to list them from smallest to largest. If we're given letters, we're just going to list them in alphabetical order. Okay. All right. So that is the practice problems. Let's move on and see if we can find domain and range when we are looking at the function in its equation form or its function notation. Okay. So when we start with a domain, or you think about cloud coverage, right, we assume that our function includes every x value from negative infinity to positive infinity and everything in between, unless we find it a problem, right? And the only problems that we're really going to see in this class is even roots. Let me just put over here. Problems is even roots. So like having a negative under a square root, that's a problem, right? Because even roots need to stay non-negative, because otherwise we get complex numbers, right? And we have issues with denominators. If we have a denominator, we know that it cannot equal 0. Okay, so these are the only two problems we're really going to look out for right now in this class. And so if we don't have these problems, if we don't have these restrictions, then our domain would be interval notation, right? All real numbers. Or we can write it in set notation. Now, set notation is something you will see in my math lab. I'm not going to ask you to write set notation for an exam or for the final or anything like that, but I do want you to be familiar with it in case you see like multiple choice problems where the solutions are given in set notation. I want you to be familiar with it, okay? What we're going to use is interval notation. So we're going to assume the answer is always negative in infinity to infinity unless we have one of these two problems. If we have one of these two problems, okay, then we're going to have to do some tweaking of our domain to make sure that it accommodates these problems. Okay, so let's look at some examples. First one, do I have an even root, like a square root or a fourth root or an eighth root? No, right? Okay, so I don't have the number one problem. Number two problem, do I have a denominator? And here I do. Since my denominator contains a variable, I know that the denominator's value could change. So I want to make sure that this denominator never equals 0. So I know that 3x minus 12 cannot equal 0. So I'm just going to go ahead and solve it so that I know what x can't be. So I'm going to add 12 to both sides, which gives me 3x can't be 12. And then if I divide off that 3, then that means x can't be 4. So x could be anything, it just can't be 4, right? So when I say it can be anything except 4, I'm saying it can be anything from negative infinity to positive infinity, but I need to take out 4. So the way that we would write that is from negative infinity up to 4, and then we take it out with a parenthesis. Remember, brackets means it can equal 4. Here, it can't equal 4. So we're going to use a parenthesis to take it out. So this says it can be anything from the negative direction up to 4, but it could also be anything on the other side of 4. So we use this union symbol, which looks like a capital U that means or. It can be anything from 4 to positive infinity. Okay, so this is our interval notation that basically says it can be from negative infinity to infinity minus the 4 that we took out with parentheses. Okay, now set notation, this one is interval notation. Set notation is a special math way of writing a whole lot with some shorthand. So set notation, set means we're going to use little squiggly lines, right? And then we just put whatever variable we're dealing with. So here we're dealing with an x, so we're going to say the set of all x's such that there's two stipulations. One is that it has to be a real number, and two, it's whatever stipulation we come up with. In this case, that it can't be 4. So instead of having to write out all x's such that they are a real number and they can't equal 4, because that's a whole lot to write, we have some little symbols that mean the same thing, okay? So the set of all x's such that, for such that, we use a line, okay? The set of all x's such that, to say x is a real number, we use an x, and then we use the little epsilon symbol, and then a double bar r. This means that x is an element of the real number system, okay? So the set of all x's such that x is a real number, and then we use a comma to represent and, we put in our stipulation. X cannot equal 4. Okay, this is our set notation. So this is one way to write the answer. This is the other way to write the answer. Okay. Everybody kind of okay? Again, I am not going to require you to write it like this on exams or the final or anything like that. But if my math lab gives you multiple choices for your solution, it may be written like this. So I want you to be aware of what that means. Okay. All right, let's look at another one. On this second one, we're looking for our problems. Do we have negatives under, or sorry, not negatives. Do we have even root radicals? Do we have a square root, a fourth root, an eighth root, a 12th root, any kind of even index radicals? And here we don't, right? We just have an x cubed and a square and a absolute value of x. Okay, so we don't have the number 1 problem, and we look for the number 2 problem. Do we have a denominator? Do I have anything in the denominator here? I don't on either, right? So that means I have no restrictions, because I can take any number and cube it. I can also figure out the absolute value of any number, whether it's negative, positive, or 0. So here we have no restrictions. And when we have no restrictions, that means our interval notation is just negative infinity to infinity. Interval notation. Okay? Because we have nothing that we have to adjust our domain for. Okay? And then I also want to write this in set notation. So for set notation, we would do the set of all x's such that x is an element of the reals, meaning x is a real number. And then because we have no stipulation, like on this one we had the stipulation that x can't be 4, here we don't have a stipulation. So that's it. That's just our answer. Okay? When we're writing set notation, we're just saying any real number x can be a solution. Okay? All right, let's look at the next one. First one I look for is even root radicals. So here I do have a radical, but if you notice, my root here is a 3, which is odd. And odd roots don't have any restrictions, because it's okay to have negatives under a cube root. It's okay to have negatives under a 5th root. That's something we can actually simplify. Okay, so because this is an odd root, we have no restrictions. No restrictions. So again, if we have no restrictions, my answer is going to look the same to this. It can be negative infinity to infinity, which means that we have the set of all x such that x is a real number with no stipulation. Okay? Everybody okay? All right, let's look at the next one. Do I have an even root radical? Well, if I look on the top and bottom, I don't have any radicals, so I don't have to worry about the number 1 problem. Number 2 problem is that my denominator can't be 0. So I do have a denominator here. So I want to go ahead and make sure my denominator does not take on the value of 0, and the only way to do that is to set it equal to 0. So x squared plus 2x minus 3, we want that to not equal 0. And this one's a little bit more difficult than the first example we did, right? Because it's not x to the first power that we can just isolate. It's an x squared. So here we need to factor this so that we can set each factor equal to 0 and solve. So I'm going to use my sum product technique. My sum is my middle coefficient, which is 2. My product is my first coefficient times my last coefficient. So my first coefficient is 1 times my last coefficient is negative 3. So to multiply to get negative 3, I'm going to use 1 and 3, right? But in order to get a positive 2, when I combine them, I will need a negative 1, right? Negative 1 times 3 gives me negative 3. negative 1 plus 3 gives me the positive 2 that I need. And then, because my leading coefficient is a 1, I can use my shortcut. So I know this is going to factor into x minus 1 and x plus 3. So those two factors that make up the denominator, we do not want them to be 0, right? So let's figure out what x values would make these 0. So x minus 1 can't be 0, x plus 3 can't be 0. So if I solve each of these, this tells me that x can't be positive 1 and x can't be negative 3, right? So these are my two restrictions. So again, for interval notation, I always start off with negative infinity to infinity. So I'm going to start with negative infinity, and I can include all negative numbers until I get up to my first problem. My first problem being that x can't be negative 3. So I'm going to take out negative 3, but then it can be anything from negative 3 until my next problem, which is that x can't be 1, right? Or it could be anything bigger than 1. So again, we're just saying it can be anything from negative infinity to positive infinity, but we're taking out the negative 3 and we're taking out the 1. Okay? And then in terms of set notation, we're going to say this is this set of all x such that x is a real number, and our stipulation is that x cannot equal 1 or negative 3. So we're going to say x cannot equal negative 3 or 1. Okay. All right. I want to show you one more, and then I'll have you try some stating the domain in both interval notation and set notation. Okay. All right. So this next one on page 18 looks like f of x is the square root of x. So remember our two stipulations, even root radicals and denominators. I can see here I don't have a denominator, so that's not going to be an issue. But I do have an even root, right? Because anytime I see a square root, right, if there's no number written in this little square root index spot, the implied index is a 2. So because it's even, we know that whatever's underneath our radical, remember we call that our radicand, right? So if we have an even root radical, that means that our, radicand has to be not negative. So the way we say not a negative number in math terms is that it has to be greater than or equal to 0. Because it's okay to be 0, it's okay to be positive, we just want it to not be negative so that we don't end up with imaginary or complex numbers. So I'm going to take my radicand, which in this case is just x, right? So x has to be greater than or equal to 0. Now normally once I take the radicand and set it greater than or equal to 0, I would then have to solve and get x isolated. But in this case, since x was my radicand, I don't have anything left to solve for. This is my stipulation. Okay, so if I want to write this in interval notation, this says I can use any x as long as it's greater than or equal to 0. So 0 is my starting point, right? And because it's greater than or equal to, I can include the 0 with a bracket. So anything from 0 or greater than 0. So it's going to go out to positive infinity for my interval notation. Okay, for my set notation, I do the set of all x's such that x is an element of the real number system and x has to be greater than or equal to 0. Okay. So we just go ahead and leave our answer like that. All right, so there are 3 for y'all to try. So go ahead and pause the video and figure out what the domain is. Make sure you write the domain both in interval notation and set notation. And then when you're ready to check yourself, go ahead and pause or unpause or play the video and we'll see how you did, okay? All right, on the first practice problem, the only stipulation we have is that the denominator cannot be 0. So we set x minus 7 not equal to 0 and solve, which means x can't be 7. So our set notation is x such that, the set of all x's such that x is a real number and x can't be 7. And interval notation, we go from negative infinity to positive infinity, but we take 7 out with parentheses, right? On the second one, notice I don't have any even roots, but I do have a denominator. So even though the second term has no restrictions, my first term has a denominator. So I have to make sure my denominator does not equal 0. In this case, I didn't have anything to solve for. It's just x can't be 0. So that means that's my stipulation that I'm going to put in here for my set notation, and that is also the value that I have to take out of my interval notation. So negative infinity to infinity, but taking out 0. Okay, and then on our third one, this one also has a denominator. Our denominator cannot equal 0. Here we use our sum product chart to figure out that this factors into x minus 5 times x minus 2. Since that can't equal 0, we set each one equal to 0 to figure out what x can't be, which in this case is 2 or 5. So in our set notation, our added stipulation in here is that x cannot equal 2 or 5. And in our interval notation, we're going to go from negative infinity to infinity, but we need to take out the 2 and we need to take out the 5. So we should end up with 3 different little intervals for our domain solution. Okay? If you need to see that again, feel free to go back and watch the video. I know I talked through it kind of fast, but we want to get through one more thing, which is evaluating functions. That's the last part of this section. And evaluating means we're just plugging things in, right? We're taking whatever they give me and we're plugging them into the function. Okay, now we do have to consider our domain. We know how to find domain. So if our function has a restriction, like say x can't be 17, right? Or something like that. Then if they tell us to find f evaluated at 17, we know it does not exist, or it's not going to be something we can actually work out and get a good answer to. So if that happens, you can write does not exist, or you can also write undefined. Okay. All right, so first thing I look at when I'm doing one of these evaluating functions problem is I look at my function and ask myself, does it have one of those two problems? Do we have even roots? Do we have denominators? If so, I need to figure out what my restrictions are. Here, I don't have any radicals at all, right? And I don't have any denominators. So that means my domain here is negative infinity to infinity. So I have no issues. So if I have no issues, I should be able to plug in all of these things and get a nice pretty answer, right? All right, so let's go ahead and plug in f of negative 1. So remember, when we talk about function notation, f of x or g of x or whatever of x we're talking about is the same thing as y, okay? So when we see f evaluated at something, whatever is inside the parentheses is our x. Once we plug it in, whatever we get as our solution is our output or our range value, which is our y, okay? So this is saying we want to plug in negative 1 for x. So everywhere I see an x in my original problem, that's where I'm going to put a negative 1, okay? So in other words, I'm doing 3 times my input squared, so negative 1 squared, minus 2 times my input, so 2 times negative 1, plus a positive 1. So all I did is just rewrite this function, but everywhere I see an x, I'm putting in my input value. And then from here, I just simplify. Okay, I do my exponent first, so negative 1 squared is positive 1, so I have 3 times 1. Negative 2 times negative 1 is positive 2, and then I have a positive 1. And then I just keep simplifying. 3 times 1 is 3, plus 2 plus 1 is going to give me 6, right? So what this is saying is when I plug negative 1 in for x, what I'm getting out for y is 6. Okay, so there's a few ways to express your solution. I'm fine with you just saying that equals 6 and boxing in the 6. In my math lab, they might represent it like f of negative 1 is equal to 6. They might write it like that as a solution choice, or they might write it as an ordered pair. Remember, what went in was my x, what I got out was 6. So they might give you a solution point negative 1, 6. Okay, so all of these mean the same thing. No matter what, we're plugging in whatever they gave us in the parentheses, and what we get out is our solution, or what it's equal to, or our second coordinate. Okay, let's look at another one where we're just plugging in a regular number. Okay, so here we're plugging in 3 for x. So everywhere we see an x in our original function, we're going to put a 3. our function says to do 3 times our input squared. So we're going to do 3 times our input, which is 3, squared, minus 2 times our input, so minus 2 times 3, plus 1. Okay? And then again, we're just simplifying. So 3 squared is 9, so I have 3 times 9. And then negative 2 times 3 is negative 6, plus 1. 3 times 9 is 27, minus 6 plus 1. 27 minus 6 is 21, plus 1 is 22. So again, I'm fine with you just circling the answer like this, but if they give you one where we're evaluating nice pretty numbers like this, they might give you solution choices like f of 3 equals 22, or f of 3 equals 19, or f of 3 equals 0, and you have to choose the correct one. Just know whatever's inside, here's what you plug in, what it equaled is what you get out. Okay, or as an ordered pair, this would be 322. Okay, now we're only going to have to worry about these other ways of writing our answer when what we're plugging in is a nice pretty number. So on number 3 and 4 here, these are not ones that we would express the answer like this, because we're plugging in additional variables. Okay, so I'm going to go ahead and show you same idea, right? But this time when we plug in the letter, we may not be able to do as much simplifying, right? Same idea. Wherever I see an x, I'm going to be plugging in a negative t. So my function says to do negative 3 times my input squared. So negative 3 times my input squared, and my input is negative t. The next term is negative 2 times my input. So negative 2 times my input of negative t. And then my third term is just a positive 1. Okay. So we go ahead and simplify this. Negative t squared is going to make it a positive t squared. So we have 3t squared. Negative 2 times negative t makes it a positive 2t plus 1. Okay? And we're just going to leave it like that. You don't have to try to factor it. Don't set it equal to 0 and solve. All we wanted to do was plug in negative t and see what it simplifies to. Okay? Same thing with this next one. We're going to plug in this whole quantity everywhere we see an x. Everywhere we see an x, we're going to put that ugly sucker in there. So if I go back up to my original function up here, my original function says to do 3 times my input squared. So my input is 1 minus t, and we're squaring it. My second term says to do negative 2 times my input. So negative 2 times 1 minus t. And then my third term is just a positive 1. Okay, so again, whatever's in those parentheses, that's what we're plugging in everywhere we see an x in our original function. Okay, so now we have some simplifying to do. So a squared quantity, we cannot square 1 and square t and call it good. A squared quantity means I have 2 copies of that quantity. So I'm just going to rewrite this as 3 times 1 minus t times 1 minus t. And then I'm going to go ahead and distribute this negative 2. So that gives me negative 2 plus 2t, and then the positive 1. Okay. Now in simplifying this, I always like to distribute this first. Distribute the quantities, and then whatever that equals, then we'll multiply this 3 into it. So I'm going to leave the 3 outside for just a minute and distribute this out. 1 times 1 is 1. 1 times negative t is negative 1t. Negative t times 1 is negative 1t. And negative t times negative t is positive t squared. Right? Minus 2 plus 2t plus 1. And now I can distribute this 3 into all of these terms. Okay? So 3 times 1 is 3. 3 times negative 1t is negative 3t. Again, 3 times negative 1t is negative 3t. 3 times t squared is positive 3t squared. And then I have a negative 2 plus 2t plus 1. Okay? Whew! Right? So now we've got it all multiplied out. Now we just have to combine like terms. So I only have one term that is a t squared. So I have 3t squared. Then I look for my t terms. Negative 3t and negative 3t gives me negative 6t, plus another 2t is negative 4t. And then I look at all of my constant terms. So I have 3 minus 2 is 1, plus another 1 is positive 2. So this is what I get when I plug the quantity 1 minus t in to my f function. Okay. All right. So on the next page, there are 3 for y'all to try. Go ahead and simplify them as much as you can if possible. And then when you're ready, play the video again and we'll see how you did. Okay, so on number 1, when you plug in 4, you get 0 over 7, which simplifies just to 0. Okay. On number 2, we run into some issues, right? Because it wants us to find f of negative 3. We plug negative 3 and we get a 0 on the bottom of the fraction. And remember, when 0 is underneath the fraction, it's undefined. Or in other words, it does not exist. So if you worked it out and got a 0 in the bottom, you can go ahead and just say DNE for does not exist or undefined. Or if you took your function from the very beginning and noticed that it had a denominator, from what we just learned, denominators cannot be 0. So if I were to set x plus 3 equal to 0 and solve, it would tell me x cannot be negative 3. So if you know already x cannot be negative 3 and they ask you to find f of negative 3, you can just go straight to does not exist or undefined. You don't even have to plug it in and prove it, right? All right, and then on our last one, we're plugging in an ugly quantity. We plug the ugly quantity in on top and bottom. Remember, we cannot reduce here because these quantities are stuck like glue to this 4 and this 3 with the plus and minus signs. So since nothing's going on outside the quantities, we can drop the parentheses, but we're not able to reduce any further. So we just leave it like this. Okay. All right. So that is the end of section 1.2. So you should now be able to do that homework assignment in my math lab. If you have any questions, please let me know.